So we have considered separable spaces. Now let's consider another type of spaces, metric spaces, which is termed complete metric spaces. So let us consider the definition of a fundamental sequence, or also it's called a Cauchy sequence. So let, in a metric space, so consider, in a metric space, let us consider a sequence in a metric space is said to be fundamental or Cauchy if for every epsilon greater than 0, there exists a natural number such that for every n and m greater than or equal to this natural number, the distance between xn and xm is less than epsilon. Well, I believe you have seen this definition in calculus for the usual sequences in R or Rn. And you probably remember from calculus that every convergent sequence is fundamental. Every convergent sequence is fundamental. And also, you probably remember from calculus that in R, or even in Rn, every fundamental sequence is convergent. So these two definitions are equivalent. This is not the case in the general metric spaces. And this leads us to a definition. A metric space is said to be complete if every Cauchy sequence is convergent to an element of this metric space. So in general, fundamental sequences are not convergent in general metric spaces. Well, let's consider a simple example. Let our metric space be an interval 0, 1. Well, we are on R1, so the usual metric on R1. If we take any fundamental sequence from X, if we take any sequence fundamental, first of all, this sequence is the sequence of real numbers. So we are in R1. And we know that in R1, every fundamental sequence is convergent. But the question is, in this definition, we have to ask for a convergence to an element of this metric space. If we have a sequence of elements from 0, 1, and it is convergent, does it converge to an element from this interval? Yes, because it's closed in R. Xn converges to X, and this X is an element of 0, 1. Now let us consider another example where our metric space is an open interval still in R1. And let us consider a sequence Xn to be 1 on n. It is clear that this sequence belongs to our metric space. Is it fundamental? So yes, we can find, regardless of how small is epsilon, we can go for the large numbers, for the large n, the elements will be very close to each other. So this sequence is fundamental. Does it converge? Well, I will rather say, what is the limit of this sequence? It converges to 0. But does 0 belong to our metric space? No, it doesn't. So we kind of know, suppose, that we are in Rn. And so this sequence convergent in Rn. But when we are in our metric space, we do not care about anything else. We are just here, and none of the other points exist for us. So there is nothing left. So this one does not belong to our metric space. And so this sequence is not convergent in our metric space. This sequence is Cauchy, but it does not converge in X. So it tends to 0, but 0 does not belong to this set. So the elements of this sequence getting closer and closer to each other, and closer to, yes, this is a Cauchy sequence, but it does not, yes, because it goes closer and closer to 0, but 0 does not exist in this reality. We are on this interval, on the open interval, and there is no 0 included, so it does not exist in our metrics. As you might guess from the definition, or even from the name, completeness is something good. In this case, we have a very nice sequence in our metric space, but our metric space is not as good to contain the limit of this sequence. So completeness is something good. And most of the metric spaces which we have considered before are complete. So let me just mention a few of them and prove completeness for some of them. Example. Well, Rn with P metric is complete for any natural number n and any metric, any p between between 1 and infinity, including 1, including infinity. In this one, it's easy to figure out this because we already seen that if we consider in these metric spaces, if we consider a ball centered at a point and of radius half, then this ball is just the point itself. So if a sequence is fundamental in this space, that it eventually equals to exactly the same element, and so it is convergent. Let's consider one more example of continuous functions. Continuous functions on an interval with the infinity metric. So the metric supremum, let me recall it. So rho infinity of between f and g is well, continuous function, so it's maximum. Let's prove that it is complete. So let Fn be a Cauchy sequence. For every epsilon greater than 0, there exists a natural number n such that for every m and n greater than or equal to n, we have that the metric, the distance from Fn to Fm is less than epsilon. So maximum of Fn of t minus Fm of t is less than epsilon, and the maximum is taken over all t. Which means that this expression is less than epsilon for every t. For every n m greater than or equal to n, and every t from the interval a, b. So this expression less than epsilon holds uniformly in t, which means that this sequence converges uniformly. Converges uniformly. Yes. So this function converges uniformly to a continuous function. the limit belongs to our metric space of continuous functions. So our metric space is complete. Let's consider again the set of all continuous functions on the closed interval, but now the metric will be not rho infinity but rho 2. I will leave it for you as an exercise to construct an example of the sequence of continuous functions which converge in this metric rho 2, but it converges to a discontinuous function. We have introduced the definition of complete space, complete metric space. Consider several of examples. So it's good to have a criteria for the metric space to be complete, some verifiable criteria. And well, we do have it. Theorem. A metric space is complete if and sequence of closed balls, any decreasing sequence of closed balls with radius tending to 0, with radius tending to 0, has a non-empty intersection. Let us start with the case when the metric space is complete, and then consider a decreasing sequence of closed balls with radius tending to 0 and show that it has a non-empty intersection. So let a metric space be complete. Let it be complete, and let Bn, well, be the sequence of our closed balls. Be such that, well, first of all, we need it to be decreasing. By decreasing, we mean that every consequent ball is a subset of the previous ball. So this is decreasedness. Well, the balls are closed. All of them are closed, and their radius tending to 0. Rn tends to 0. We want to show that the intersection of all of these balls is non-empty. We have supposed that X is a complete metric space. So for this metric space, we know that any fundamental sequence is convergent. So let's try to use this fact. So first of all, let's introduce a sequence. Let Xn be a center of a ball Bn. And I claim that the sequence Xn is fundamental. We have the distance between Xn and Xm, let's suppose for every m larger than n, so Xn is a center of the ball Bn, Xm is a center of the ball Bm, and m is larger than n. Using this condition, we know that the ball Bm sits inside the ball Bn. So the distance between these 2 points, so both of these points are in the ball Bn. So the distance between 2 of them is at most 2 radius. Well, in fact, it's less than radius because Xn is the center of the ball Bn, but it doesn't matter for us much. So the point is that this estimate tends to 0, which means that this distance can be made arbitrarily small, which means that the sequence Xn is fundamental. The sequence Xn is Cauchy. Okay, we have constructed a Cauchy sequence, and since our space is complete, we know that this sequence converges to an element of this metric space. So this sequence is convergent to an element of our metric space. We have that a ball Bn contains all elements of a sequence Xn except the first n minus 1, except x1, x2, and up to x minus n, xn minus 1. So any of these balls contains all the elements of our sequence starting from some number, in particular starting from n. But this sequence is convergent, so all of these balls contains the limit of this sequence. So X belongs to all of these balls, so it belongs to the intersection. And so the intersection is non-empty. The first part of the proof is done. Any questions? Let's go for the second part of the proof. And for the second part of the proof, we consider a contrapositive statement. Contrapositive statement. So we will prove that if X is not complete, then there exists such a sequence of balls satisfying all the conditions with empty intersection. So what we will prove is if X is not complete, then there exists a decreasing sequence of closed balls with radii tending to 0 with empty intersection. With empty intersection. So we have supposed that X is not complete, which means that there exists at least one fundamental sequence which does not converge to an element of X. So let's consider this sequence. Since X is not complete, there exists a Cauchy sequence xn which does not converge to an element of X. Which does not converge to an element of X. But since this sequence is Cauchy sequence, we do have control on the distance between the elements of this sequence. So for instance, since this sequence is Cauchy, there exists n1 such that for every m greater than n1, we have the distance between xn1 and xm is less than half. So our first closed ball is centered at xn1 and it is of radius 1. Again, using the fact that our sequence is a Cauchy sequence, we can find n2 there exists n2 such that for every m greater than n2, the distance between xn2 and xm is less than 1/4. And let our second ball be a ball centered at x and 2 and of radius half. Also, we want to prove that the sequence we construct will be a decreasing sequence. So we need to show that B2 sits inside B1. This is what we want to prove. Let a point y to be an element of B2. We want to find the distance between x and 1, the center of the ball B1, and y. By a triangle inequality, we have that it's less than or equal to x and 1, x and 2, plus the distance between x and 2 and y. The distance between x and 1 and x and 2 is less than half by assumption on x and 1. And the distance between x and 2 and y is less than half because y belongs to this. So it equals to 1. So we proved that B2 sits inside B1, which is fine with us. By continuing this process, we will obtain a sequence Bn we obtain a sequence, a decreasing sequence. Decreasing sequence of closed balls of ready one over 2 to the power of n 2 to the power of n minus 1. Let x belongs to x is not good. Oh no, it's fine. Let x belongs to the intersection of all of these balls. X is the limit of the sequence xn. If we assume that the intersection of all these balls is not empty, so it contains some element x, then by construction, this element is a limit of the sequence. We assume that this sequence fundamental and this sequence does not converge to an element of x. But there is x is a limit of this sequence, so we have to that x does not belong to the vector space. The intersection is empty. Yeah. And we're done. So we have a criterion for the completeness of a metric space. Let's speak a little bit more about non-complete metric spaces. If we consider the set of rational numbers with the usual metric on R1. Is it a complete metric space? We take rational numbers with the usual distance on R1. Is it a complete metric space? No. With no problem, we can find a sequence of rational numbers converging to irrational number, which does not belong to this one. So this set is not complete, but we know that the closure of Q Q is dense in R, and R is complete. R is complete. And the natural question is it just a peculiar situation that we've taken a non-complete space and we are able to found a complete space, a larger space, which is complete and such that our initial space is dense in this one? And it turns out that it is the general situation. Definition. Let X be an arbitrary metric space. Be an arbitrary metric space. A complete metric space prime, rho prime, so some other metric space, some other metric, some other set, some other metric, is said to be a completion of X if the closure of X equals to X prime. Or rather, let's, yeah, it's fine. So, which means, by the way, that X is dense in X prime, as in the previous example, where we have to specify the closure is taken with respect to the new metric, rho 1. So this closure of X is taken with respect to the new metric. Because, well, if we take the closure of X with respect to its own metric, then it will be the same result, because every metric space is closed. So now we will prove a theorem which tells us that any metric space has a completion, and moreover, this completion will be unique up to isometry. But before we go for a proof, in the proof we will use the notion of equivalence relation. Some of you might know that. I will briefly recall what is relation and what is the equivalence relation on the set. Relations. Definition. A relation R, set X is nothing but a subset of X times X. So a relation is just a subset of some pairs of elements of the set X and nothing else. So further, since it's a subset, so if some pair AB belongs to R, we will write A is related to B. There are several properties which relations can satisfy or cannot. So let us say that a relation R on X is reflexive when A is related to A for any A from X. So any element of the set is related to itself. Symmetric. When A is related to B implies B is related to A again for any B, A and B from the set. So this is the symmetricity. And one more property which we will discuss is transitivity. A relation is transitive when A relates to B, B relates to C, and B relates to C. This implies that A relates to C again for every A, B, C from our set. And well, if a relation satisfies all these three properties, we will call it an equivalence relation. A reflexive symmetric and transitive relation is called equivalence. Is called equivalence relation. In this specific case, instead of writing R, we will write an equivalent sign. We write A equivalent to B, well, if they are related. For equivalence relation, we can define so-called equivalence classes. So for any element from a set, an equivalence class defined as follows. So we will denote the equivalence class like an element generating the class and in square brackets. So it is a set which consists of all x's from the set such that x is equivalent to a. That's an equivalence class. So an equivalence class generated by A consists of all elements which are equivalent to A. It is fairly straightforward from this definition and from the definition of equivalence relation, so it satisfies these three properties, that if we have two equivalence classes for any equivalence classes, we have, so any two equivalence classes either disjoint so they either disjoint, do not have any elements in common, or coincide. So we will denote by a factor equivalence the set of all equivalence classes. So all possible equivalence classes of A. Since we already know that any two equivalence classes either coincide or disjoint, the set of all equivalence classes form a partition of A. Where X itself an equivalence class from the set of all equivalence classes. Let us consider one example of equivalence relation on a set. So, example. Let A be the set of all triangles on a plane. So the set of all possible triangles on a plane. I will say that two triangles for A, B from A. So little a and little b are triangles. So for two triangles, I will say that they are equivalent if they have the same area, the equal area. It is easy to see that this relation is an equivalence relation. We consider a set, and on this set we consider the collection of all possible sequences. I will call two sequences from Sx I will call them equivalent if they have the same limit. If they have the same limit. Well, it is in fact an equivalence relation. Well, after the warm-up, let us state and prove the theorem which tells us that for any metric space there exists a completion, and moreover this completion unique. For every metric space X rho, there exists a completion so another metric space. What is the difference between complete and non-complete metric space? In a complete metric space, every fundamental sequence converges to an element of this space. If the space is not complete, then there is a fundamental sequence which converges, but the limit of this sequence also does not belong to the space, does not belong to the metric space. And so you might say that what's the problem with completion then? So for instance, if we have an interval 0, 1, an open interval, this considered as a metric space, say in R1. This metric space is not complete, but if we add points 0 and 1, then it will be a complete set. So if we just take a closure of our set, then we will get a complete metric space. The problem here is that we don't know the ambient space where to take the closure, because the metric space itself is closed. It's always closed. So the interval 0, 1 considered as a metric space is closed. It's an open subset of a real line, but it is closed in itself. So we cannot simply take a closure. So we have to figure out something. But the idea is behind the construction of the completion is pretty much to take the closure of a metric space. Okay, proof. Let X rho be an arbitrary metric space. And let F be a collection of all fundamental sequences from X. Using our previous example, we will call two sequences equivalent if they have the same limit. two sequences, fundamental sequences from F, equivalent and well, we will write the usual equivalence if they have the same limit. Well, from the previous example, as we previously discussed, this relation is in fact an equivalence relation. So we can split the set F into the equivalence classes. And we will set X prime to be F factor equivalence. So we take all possible equivalence classes. This will be a candidate for our metric space, for our new metric space, which will be a completion. So there are quite a lot of things to prove, because we want X prime to be a metric space, but so far it is just a set. So first of all, we need to define a metric on it. So let's try to do this. For any x prime, y prime from the set x prime, so we know that this x prime and this y prime are in fact equivalent classes. So they are classes of sequences. So for any of these, we can find a sequence from the class, so a representative sequence. So there are two fundamental sequences such that the first sequence belongs to x prime, so to the first equivalence class, and the second sequence belongs to the second equivalence class. So we've taken, for any two classes of equivalence, we just take one sequence from that class, and we will use that sequence as a representative of the class. And we set rho prime between x prime and y prime to be the limit of rho, the old metric, between xn and yn. So this is how we introduce a function which we want to show, and we want to show that it is a metric. But before to prove that this function is a metric, we have two more problems to solve. First of all, we write in limit over here. Why does this limit exist? So that will be the first problem to deal with. The second problem, to find, we define a distance between two equivalence classes by finding a representative in any of these classes. Why does this distance depend on the representative which we choose? Well, we will show that it does not. So first of all, we need to show that this function is well defined. Rather claim rho prime is well defined. First of all, let us show that the limit exists. Since we know that any two representatives we choose are fundamental sequences, let us use this information. So since both sequences x and y are fundamental, which means that we can choose a small enough number epsilon and then find m and n large enough such that we do have control in a distance. So since they are fundamental, take m and n large enough. Large enough. And consider the difference rho of x n y n and rho x m y m. This can be estimated by rho of xn ym. Let's start with the first term. Then I will subtract rho xn ym So to this expression I added and subtracted this term and split it in two. I added and subtracted this term and used the triangle inequality for the absolute values. Further, in this first difference, we have xn and xn here. So we can use the triangle inequality to estimate this as a distance between yn and ym. And the same story here. So for the first term, we have that it is less than or equal to the rho of yn ym. Plus rho of xn xm. But we know that sequences x and y are fundamental. So the distance between yn and ym can be estimated in terms of epsilon. So say it is less than epsilon over 2, and this one is less than epsilon over 2 as well. So we can choose any epsilon, then take epsilon over 2, find some large m and n such that this will be true. So what we showed is that this sequence, the numerical sequence, let me call it Sn, which equals to rho of xn yn. Hence, this numerical sequence is Cauchy. The sequence is numerical, which means that the elements of the system, or the elements of a sequence, are real numbers. Since the set of real numbers, well, with the usual metric R, 1 on infinity R, is complete to some real number. So in the definition of our function rho prime, the limit exists. So this limit exists. For the well-definedness of rho prime, we also need to show that the definition does not depend on the choice of the representative. So to do this, let's choose two different representatives from each class and show that the value of the function rho prime will be the same. Further. Let's take two sequences, x and x1, from the class x. Was that the definition? From the class x prime. Take two representatives from the first class and two representatives from the second class. So what I want to show is that the function rho prime, the value of this function, does not depend on whether we take xn and yn or xn1 and x and yn1. So it doesn't matter. So let us consider then the difference between xn, the distance between x and yn, and subtract the distance between xn1 and yn1. As previously, I will add and subtract a mixed term and then split it. Loss. As before. So I have just added and subtracted these two terms and then split it using the triangle inequality. Using the triangle inequality for the absolute values. Now I will use the triangle inequality for metric to write it as rho of yn1 plus rho of xn xn1. But what do we know about xn and xn1? We know we've chosen them from the same equivalence class. So xn and xn1 are equivalent. So the limit of the distance between them tends to 0. And the same for y. Yn and yn1 are from the same equivalence class. So they are equivalent. And by definition of our equivalence, this distance tends to 0. So this sum tends to 0 as n tends to infinity. So what we did, we considered the value of, we considered the distance between two representatives and then the distance between two other representatives and proved that this difference between two of them tends to 0, which means that combining all of these, this means that rho prime is well defined. Rho prime is well defined. We have proven that rho prime as a function rho prime is well defined. Now the aim is to show that rho 1 is metric. This is not as difficult. So another claim, rho prime is a metric. Let's start with the first axiom. Rho prime of x prime y prime equals to limit of xn yn rho of this limit. For some representatives, xn is from the equivalence class of x prime, yn is from the equivalence class of y prime. So in the first axiom, we need to prove that if the metric is 0, then the two elements coincide. By our definition of the equivalence, if limit of this expression is 0, then these two sequences are equivalent by our definition of equivalence. So this is if and only if xn equivalent to yn. But the equivalent sequences belongs to the same equivalence class. But we've chosen xn to be from this equivalence class and yn to be from this equivalence class. But they're equivalent to each other, so they are from the same class. So the initial two classes then coincide. That is the first axiom. The second axiom is trivial, as in most cases. If you swap the equivalence classes, then you just swap the representative sequences, and yeah, you get the result. Triangle inequality. Let's take three equivalent classes. Equivalence classes. And consider the left-hand side of the triangle inequality. Writing these two expressions down by definitions, we obtain for some representative sequences xn, yn, and zn. Well, limit is a linear functional. So the sum of the limits equals to the limit of the sum. And now we will use triangle inequality for the metric rho. which is nothing but rho prime of x prime z prime. So we conclude that rho prime is a metric on the set x prime. So x prime rho prime is a metric space. At this point, or even earlier, you could have asked me, why on earth do we do this? So we want to construct a completion of our metric space. But our metric space X consists of points. We constructed another metric space, but what are the elements of this metric space? The elements of this metric space are classes which are sets of functions, but we want our initial metric space X to be dense in this one, in the completion. So first of all, we need to show that our metric space X sits inside this new metric space X prime. So let me first write it down, and then we will discuss how is it possible. Again, let me say it again. So elements of this space, so it is a set of points. We do not care much about the nature of these points. It can be sequences, functions, but we call them points. What do we have here? A set of subsets of sequences. Well, these sequences consist of elements from X, but anyway. So it looks like these two sets are of completely different nature. How can we even speak about the inclusion? The key point is, the key idea here is to use the notion of isometry. As you remember, several lectures ago, we discussed an isometry, and we agreed that if two sets are isometric, regardless of their nature, we think about them as being the same. So what we will do now, we will construct an isometry from X into X prime, so the distance preserving mapping. And upon doing this, we will say that X can be identified with some subset of X prime. So first of all, let us quickly note that if we take any point from the set X, then out of this point we can construct a sequence, a constant sequence. Every element of this sequence will be our element, our point X. A sequence xn such that xn equals to x for every n. A constant sequence. So it's not just any sequence, it's not just a sequence, it's a fundamental sequence. Constant sequences are fundamental. And now, having a sequence, we can consider an equivalence class generated by this sequence. And consider x prime to be an equivalence class generated by this sequence. X prime, in the way we constructed it, x prime is a collection of all sequences converging to x. So now, let us consider a function phi from x to x prime given by phi of x equals to x prime. X prime is this equivalence class which we constructed from x. Let us now prove that the function phi which we introduced is isometry. Let's take 2 points from x and consider the distance between the images. By definition of the function phi, this is just the distance between x prime and y prime, which are constructed from the constant sequences. By the definition of function rho prime, we get that this is the limit of rho xn yn, where xn is some representative of the class x prime and yn representative of the class y prime. But we can take any representative. We proved that the value of the function does not depend on the choice of the representative. So let's take for xn the sequence which is constant and equals to x, and for yn we will take a sequence which is constant and equals to y. Which is nothing but rho of xy. So the function phi, the mapping phi, is an isometry. So it preserves distances. Phi is isometry. Hence, sets x and phi of x, the image of x, this set is a subset of x prime, are isometric. So x and its image in x prime are isometric. And as we agreed before, when these sets are isometric, we think about them as being identical. So that's why I conclude that x is a subset of x prime. So we have already proved that X is a subset of a new metric space, of a larger metric space. We also need to prove that X is dense in X prime. Let us prove that the closure of X equals to X prime. What we will show? We will take a point from X prime and show that in any neighborhood of this point we can find a point from X, which will be the claim. So let little x prime be from the large X prime. By its nature, the element we've chosen is is equivalent class. So there exists a fundamental sequence the set of fundamental sequences was denoted by F, such that X prime equals to the equivalence class generated by this sequence. So since this sequence Xn is fundamental, let's use it. Let's use the fact that the sequence Xn is fundamental. So let me write down what we will use. So since the sequence Xn is fundamental, for every epsilon there exists n such that for every n m greater than or equal to m to n, the distance between xn and xm is less than epsilon. Now, for every n, in n, consider a sequence xm which is constant sequence and equals to every element of this sequence equals to xn. Let me write n over here to show the dependence. Now, for every of these constant sequence, I will consider an equivalence class. Xn prime to be an equivalence class generated by this sequence x with the upper index m and the lower index, so the upper index n and the lower index m. So we have a sequence of equivalence classes, and each of these equivalence class is generated by the constant sequence. What will be the distance then? The distance between xn prime and x prime. By definition, it is the limit where for the first equivalence class we take a representative. The representative is xn. For the second, we take the representative, the initial sequence we started with, xm, m to infinity. But as we already seen that, this is less than epsilon. So, we proved that in any epsilon neighborhood in the point x prime, there is a point xn prime, but this xn prime is an equivalence class generated by the constant sequence. But the classes generated by constant sequences are identified with points in x. So we conclude that in any neighborhood of x prime, we have found a point from x, which means that x is dense in x prime. One more time. So we've taken an arbitrary point from x prime, and in any epsilon neighborhood of this point we found an equivalence class which is generated by a constant sequence. But constant sequences are those who generated by a single element of x. And we identify points of x and equivalence classes generated by constant sequences. So that's why in any neighborhood of this point we can find a point from x. Done with this one. One more thing left. We need to show that x prime is complete, finally, to prove that it is a completion. Before we start the proof, let us note that if we take a sequence from x if we take any sequence from x then this sequence converges in x prime converges in a large metric space, and it converges exactly to the point little x prime, where little x prime is nothing but the equivalence class generated by this sequence. This is by the construction of this set x prime. So in fact, what we did when we constructed x prime, we took all x and added all the possible limit points of some sequences which were missing. So that's how we take the closure of this set x. Well, so first of all, if we take any sequence which could, of elements from x, it converges in x prime to an element of x prime. We want to show that if we take any fundamental sequence from x prime, that it will be convergent to an element of x prime. So let's prove this. Let's take a sequence from x prime and let it be fundamental. Let it be fundamental. So all the points of this sequence are elements from x prime. And we know that x is dense in x prime. So arbitrarily close to any element of this sequence, we can find an element of x. Take, rather, since x is dense in x prime, then we can take a sequence xn from x, a sequence xn from x, such that the distance rho prime between between xn and xn prime is less than 1 on n. Where here, when I write xn, okay, let's go even simpler. Phi of xn, to be exact, to be precise. So we take a sequence of elements from x. To any element of this sequence, I apply the mapping phi to get the equivalence class, and then I compute the distance between these two equivalence classes. But this sequence, which we constructed using this condition, this sequence xn is fundamental because xn prime is, and they are close to each other. This sequence is fundamental. I forgot to add here, when we consider this initial thing, I forgot to add that this sequence also has to be fundamental. Not every sequence converges, such that every fundamental so we add here that it's fundamental. And that one is fundamental. So that one is converges. Converges to some point, say x prime, in x prime. But this sequence and this sequence are close to each other. so the distance between the elements is less than 1 on n. So they are close to each other. So this initial sequence which we started with is convergent as well. This means that the metric space X prime is complete, and we are done with this proof. I will state one more result about the completion and leave it for you as an exercise. So the other theorem a completion of a metric space is unique up to isometry. Up to isometry. Which means that if x prime and x2 prime are completion of some metric space X, then x prime and x double prime are isometric.